Good morning, students. This lecture is in continuation with the previous lecture. Today's topic is eutectic mixtures. A eutectic mixture is defined as a mixture of two or more components which usually do not interact to form a new chemical compound, but which at certain ratios inhibit the crystallization process of one another, resulting in a system having a lower melting point than either of the components. I'll just explain you. For example, we take certain substances like menthol, thymol, camphor, phenol, cellol, etc. When we mix them, when mixed in a particular proportion, they tend to liquefy due to reduction in their respective melting points. Mixture of such substances are known as eutectic mixtures. Eutectic, it's a Greek word. Eutectic means easy melting. Okay. Eutectic mixtures can be formed between active pharmaceutical ingredients, between APIs and excipient, or between excipients, thereby providing a vast scope for its application in pharmaceutical industry. Now there are various factors which govern the formation of eutectic mixtures. Number 1, the components must be miscible in liquid state and mostly immiscible in solid states. Secondly, intimate contact between eutectic forming materials is necessary for contact induced melting point depression. Third, the components should have chemical groups that can interact to form a physical bonds such as intermolecular hydrogen bonding, etc. Fourth, the molecules which are in accordance to modified Van 't Hoff equation can form eutectic mixtures. Now there are various applications of eutectic mixtures in pharmaceutical industry. For example, we take pre-formulation studies before the drug is developed. During these pre-formulation studies, the compatibility studies are done between API and excipients. They play an important role in excipient selection. Secondly, testing of eutectic mixture formation can help in anticipation of probable physical incompatibilities. Means if there are any incompatibilities between the drug and the excipients, these are considered during the drug development state. Third, eutectic mixtures are commonly used in drug designing and drug delivery processes. Fourth, during manufacturing of pharmaceutical dosage form, it is extremely necessary to anticipate the formation of eutectics and avoid manufacturing problems. For example, there are various manufacturing problems that takes place in the tablet compaction process. The heat produced in the punches and dice cavities may lead to fusion or melting of tablet powder compacts, leading to various manufacturing defects. So these are considered at the time of the drug development. Fifth, during pharmaceutical analysis, understanding of eutectic mixtures can help in identification of compounds having similar melting points. The compounds which have similar melting points, during the analysis process, the understanding of eutectic mixtures help in the identification of compounds. Okay, the compounds having the similar melting points as a rule will have different eutectic points with a common other component. Okay, now this is the table 1 which shows the applications of various eutectic components in pharmaceutical industry. For example, the eutectic mixture of curcumin, nicotinamide, its 10-fold faster IDR drug release and 6 times higher area under curve as compared to crystalline curcumin. For example, you can see ibuprofen, thymol, next is borneol, menthol mixture. You can see in this slide there are a mixture of various eutectic mixtures and their applications you can study. Next are the application of eutectic mixtures in the formulation development. In F&D means formulation and development में eutectic mixtures की क्या applications है? For example, allobarbital, ergotamine, imipramine. Their applications are given over here. Next topic is gases. Students, you know what are gases? Gases are all around us. Okay, you can see in atmosphere there are number of gases on the earth. For example, you see soda, bubbles come. This is also the example of gas. fumes that comes from volcanoes, they are also mixture of gases. In balloons you can see helium gas is filled, so it is also a example of gas. Now what are gases? Gases are compressible fluid and has no definite shape. Means gases are compressible fluid, they have no definite shape. Owing to vigorous and rapid motion and resultant collisions, the gas molecules travel in random path and collide not only with one another but also with the walls of the container in which they are packed. Hence, they exert a pressure. Gases exert a pressure, a force per unit area, which is expressed in dynes per centimeter square. Pressure is also recorded in atmosphere or millimeters of mercury because of the use of barometer in pressure measurement. And another important characteristic of gas is its volume. Volume is expressed in liters or cubic centimeters. The temperature involved in the gas equation is given according to the absolute or Kelvin scale. 0 degree on the centigrade scale is equal to 273.15 Kelvin. There are various properties of gases. As you can see, a sample of gas assumes both the shape and volume of the container. Gases have no definite shape, but in the container in which they are packed, the gases assume the shape of the container. The gases are compressible. The densities of gases are much smaller than those of liquids and solids. Gases form homogeneous mixtures with one another in any proportion. Now there are various gas laws. First is Boyle's law. This law states that the pressure of the fixed amount of gas at a constant temperature, that is P, is inversely proportional to the volume of the gas. Means P is inversely proportional to V, that is volume of the gas. Charles' law. This law states that the pressure of a fixed amount of gas at a constant as a fixed pressure, the volume of gas, means pressure is fixed at a fixed pressure, volume of gas, that is V, is directly proportional to the temperature of the gas. Third is Gay-Lussac's law. This law is a special case of ideal gas law. This law applies to the ideal gases held at constant volume, allowing only the pressure and temperature to change. Means P1 upon T1 is equal to P2 upon T2. Fourth is Avogadro law. This law states that the volume of a sample gas is directly proportional to N, that is the number of moles in a sample at constant temperature and pressure. Means V is directly proportional to N. V1, or you can say that V1 upon N1 is equal to V2 upon N2. Next is kinetic molecular theory of gases. You should understand this theory also. The basic assumption of this theory are: the volume occupied by the individual particles of a gas is negligible compared to the volume of the gas itself. The particles of an ideal gas exerts no attractive forces on each other or on their surroundings. Gas particles are in a constant state of random motion and move in straight lines until they collide with another body. The collision exhibited by gas particles are completely elastic. When the two molecules collide, total kinetic energy is conserved. The average kinetic energy of gas molecule is directly proportional to the average absolute temperature only. This implies that all molecular motion ceases if the temperature is reduced to absolute zero. That's all for today. Thank you.